So today we'll solve basically mathematics gate 2022 question from ODE. We'll solve question number 19 and 20 for the course ordinary differential equation. Okay, let me present. Okay, so I will play the video. Please let me know, can you hear the audio or not? Is the audio is
Okay.
fine?
So today we'll solve mathematics gate 2022 question from ordinary differential equation.
Yeah, okay.
This is the question number 19.
So let me start from it.
So today we'll solve mathematics gate 2022 question from ordinary differential equation. This is the question number 19. It's saying that the initial value problem, it is that dy by dx equals to cos xy for x is in r and y at the point 0 is y naught, where y naught is a real constant, has unique solution, first option, and the other option saying exactly two solution or infinitely many solution or no solution for this initial value problem. Okay, let's solve this one. And so in order to solve this, so this is the NPTEL reference, you can look at it. Okay, so we will first state one global existence and uniqueness theorem, from where we will deduce this result. Okay, so what is this existence and uniqueness theorem says? This is basically global existence and uniqueness. And uniqueness theorem. So it is saying that let fxy be a, so two assumptions are given. Assumption one is this is function be a continuous as a function of two variable, so this is option one, assumption one, and assumption two is the function is Lipschitz with respect to the variable y. So Lipschitz continuous in y, mean the second variable. So what is this Lipschitz condition? It is saying that mod of f of x y1 minus f of x y2, so this should be less than equals to some constant times mod of x y1 minus y2, and where x will lie in the, where x belongs to some region AB and y belongs to the whole real line, right? Means y1 and y2 should be, so therefore y1 and y2 also in the whole real line. So this should be true if a less than x naught less than b, then the OD, the corresponding ordinary differential equation, what is the OD? dy by dx equals to f of xy, and the initial condition at some point x naught it is y naught. Then it is saying that if fx is continuous in both variable and Lipschitz continuous in second variable, and then this ODE has a exactly one solution, mean unique solution, has exactly one solution, y equals to some yx on the interval where you are talking about a less than x less than b. So mean the all x in AB. So that's why it's saying that global existence and uniqueness theorem. So therefore in our case, what is, so our case it is dy by dx equals to cos of xy, and y at the point 0 is y naught. Right, so we have here we have what we have, dy by dx equals to cos of xy, right? So this is the fxy, and y at the point 0 is y naught, and x is in real number, right? So here fx is cos of xy, so we have, so note fxy here is cos of xy. So clearly this is a trigonometric function, right? So this is a continuous in all R2, so it is also both jointly continuous. So cos of xy is continuous on R2, right? So this is continuous function in whole R2 and as a jointly continuous. Right, and the second option we have to check that this is Lipschitz. So that we have to prove that cos of xy is Lipschitz continuous. With respect to the second variable, right? So in order to proving this, one way to proving then some function is Lipschitz, the mean value theorem is very useful for this, so we will use that. So take 2 points y1 and y2. So we have taken 2 points, and what is saying that, so we will use the mean value theorem with respect to the variable y. So by mean value theorem, so clearly this is differentiable and continuous, right? So mean value theorem is statement is satisfied. So by mean value theorem, there exists some c in between y1 and y2, right? y1 and y2, such that what will happen, cos of x y1 minus cos of x y2. So this should not modulus, this should be less than equals to derivative. So derivative of cos of xy, so this is with respect to the y, right? So derivative with respect to y at the point c. So let me write as a f del f by df, or del f, let me write here fx is cos of xy with respect to y at the point x comma c, right? And y1 minus y2. So from mean value theorem we will get this. And what is del f by del y? here del f by del y at the point x comma c, what it will be? It will be derivative of cos of xy, right? So it will be minus x sine xy at the point x comma c. So therefore it is minus x comma x sine cx, right? Therefore by taking mod, what you will get? Cos of xy1 minus cos of xy2. So this will be modulus of x sine cx into mod of y1 minus y2. Now let's take x to be some AB. Now let x belongs to on some interval AB, some fixed compact interval, right? Then what will happen? Cos x y1 minus cos x y2, this should be less than, so mod, so this will be mod x which is less than b, so it is b, right? So mod b, and mod sine cx, it will be mod sine cx, so this is less than 1, right? Into mod y1 minus y2, so this is less than mod b times mod y1 minus y2, so which implies cos of xy is Lipschitz on AB, right? And y is, it is y is in whole real number, right? On x belongs to this and this, right? So therefore we have satisfied the condition 1 and 2 for this theorem. So therefore we can say that, suppose we have also taken x to be such that 0 contains this interval, 0 belongs to AB. We have taken some interval so that 0 contains it, and we have given that the initial condition is given at y0 equals to y0. So by this theorem, then this OD has exactly what? One solution for all x in AB. Therefore, by the above theorem, the initial value problem has unique solution on x belongs to AB such that 0 contains the interval and y is in R, right? And now note that this AB is arbitrary, right? Now note here this interval AB, where AB are arbitrary, so that it will contain 0, the interval AB are arbitrary. So therefore the theorem is true for any sub-compact interval, right? So which is same as saying that this has a means unique solution for all x in R, right? So why? Because suppose this does not have a unique solution in some way, so you can always take some compact interval containing that where this is not, you are assuming where this is not unique, then it will violate that theorem, because because this is true for any compact set AB which contains 0. So therefore it has unique solution on R, right? So basically what? The unique solution exists let me call it 1 star. So unique solution exists for star on any AB, right? On any interval AB 0, so that this contain this, and where AB are real number. So which is same as saying that this has a unique solution on all R, right? Which implies star has unique solution for x belongs to R and y also belongs to R, right? Because suppose it does not have a unique solution on somewhere, then you can always find an interval which will contain that particular set. So there it will violate because this is true for any compact interval, there must have a unique solution, therefore it cannot happen. So it has a unique solution on all x in R. So therefore which option is correct? So this has a unique solution, so the first number, option A is correct. This initial problem has a unique solution. Okay.
Okay. So any doubt with this question number 19? No questions? Okay, so therefore, so move to the next question, question number 20.
Okay, so today we will solve mathematics GATE 2022 question from ODE. This is a question number 20. It is saying that if the eigenfunction corresponding to distinct eigenvalues of lambda of the Sturm-Liouville problem, the following, this one, with periodic boundary condition. It is saying that if the eigenfunction of this Sturm-Liouville problem are orthogonal for different eigenvalues lambda with respect to the weight function w, then you have to find what will be the weight function. So 4 options are given. You have to find among which will be the correct option. Okay, so in order to solve this, so this is the NPTEL reference. You can look into it. Okay, so let's solve this problem then. So what Sturm-Liouville problem is given. So let me first write that any general form for the Sturm-Liouville problem. So this is Sturm. Problem with periodic boundary condition. Right. So this is the general form. Any Sturm-Liouville problem with periodic boundary condition, you can write like this: d dx of px dy dx plus qx y equals to lambda times wx y, where x is in some ab, and the boundary condition y naught and at the point y pi this is 0. So at the point 0 and pi this is or some ab, right? It will be here ab. It is 0, means that's why it is called periodic boundary condition. Here wx, this is called the weight, and yeah, so this is the general form for the Sturm-Liouville problem with eigenvalue, Sturm-Liouville problem corresponding to the eigenvalue lambda. So there is a theorem. It is saying that if the two eigenvalues are different, then the corresponding eigenvalues are orthogonal with respect to this weight. If you can write like this, then the corresponding eigenvectors means solution eigenfunctions corresponding to different eigenvalue are orthogonal with respect to this weight. So this, let me write the theorem. Let v1 and v2 be eigenfunctions of, let me call this to be the star corresponding to distinct eigenvalues lambda 1 and lambda 2 respectively. Then what it is saying, then v1 and v2 are orthogonal with respect to the weight so weight function, what is the weight function here is w. So with respect to the weight function w, so what is the meaning of this? Means the integral of v1x and v2x, so bar into wx from a to b dx is 0, right? So basically saying that the eigenfunctions corresponding to two different eigenvalues are orthogonal with respect to the weight w. If you can write like in this form, the Sturm-Liouville problem, if it is in this form, then you can say that the eigenfunction corresponding to two different eigenvalues are orthogonal with respect to the weight W. So in our case we have this Sturm-Liouville problem. So we want to write like in the form in which the theorem is stated, from where you can deduce what will be the corresponding weight function, right? So here, what is the Sturm-Liouville problem? d2y by dx2 minus 3 dy dx equals to lambda y for the range x in 0 to pi, and the periodic boundary condition is y naught at 0 and pi, this is 0. So you want to write this problem in this form, right? So we can do the other way. This we can also write in that form, then we can also compare. So this will be easier. Let's do this. So what is this general form? Minus d dx px dy by dx plus qx y is lambda wx y. So if you now differentiate with respect to by chain rule, so what you will get? Minus px d2y by dx2 minus p prime of x dy dx plus qx y equals to lambda wx y. Okay, so now assume here the px is non-zero, right? Means identically not equals to 0, otherwise then it will be some first degree differential operator. So here px is non-zero, assumption is there. So therefore let's divide it by px, by minus px. Then what you will get? Assume that here p dash x not equals to 0, px is not equals to 0 identically. d2y dx2 plus p prime x by px dy by dx plus qx by minus qx by p, right? Y equals to minus lambda wx by px into y, right? So now if you compare these two, so let me call this one, so not, let me call this one 1 and this one is 2. So if you compare equation 1 and 2, what you will get? So comparing equation 1 and 2, we get, so first is there is no coefficient, it's 1 1. Coefficient of dy by dx, it's minus 3 here, and here is p dash x by px, so therefore p dash x by px, so this is minus 3. And next there is no coefficient of in this side, so this is for the lambda, so that's in the other side, that's fine. and without lambda there is no coefficient, so qx by px is basically 0. Qx by px is 0, and the coefficient for lambda, here it is lambda y, here it is minus wx px, right? So therefore third one we get minus wx by px equals to 1, right? So from this one we can say that this is wx equals to minus px, and now we can, and from here you can say that from here you will also get, from here you will get qx equals to 0, and if you solve the first one, what you will get? So this is basically minus p dash plus px equals to minus 3. If you integrate, so integrating, you will get log of px equals to minus 3x plus, let me write this constant to be the log c. So therefore you will get px to be the c e to the power minus 3x, right? So therefore from this one you can say that wx will be, so therefore because ws is minus px, so therefore wx is minus p of x, which is minus c times e to the power minus 3x, right? So we have get, or c is some real number, right? Or c is some real number. So we have get the wx will be of the form sum, so this basically you can also write some, let's write c tilde, so basically c e to the power minus 3x, c tilde is some c is minus c tilde, so some constant times e to the power minus 3x, so this is the weight. So then this theorem is saying that if there are two eigenfunctions corresponding to two different eigenvalues, then they will be orthogonal with respect to the eigenvalue. So this weight, then weight will be c e to the power minus 3x. So therefore among which options these are correct? So 4 options are given, among which, so basically if this is, so the first one is e to the power minus 3x, second one e to the power minus 2x, e to the power 2x, e to the power 3x. So if some weight function are orthogonal with respect to this weight, because the constant is does not matter, you can always take it out. So eigenfunctions corresponding to two distinct eigenvalues are orthogonal with respect to the weight function because constant we can always ignore, because constant multiply does not matter. Weight function wx equals to e to the power minus 3x. So the answer is e to the power minus 3x. So the weight function will be e to the power minus 3, means option A is correct. Okay.
Any doubt or question from this one? Okay, fine. Yeah, other one Dasana Pillai, I think. Do you have any doubt? Okay. I think someone has asked some question from the last class. Yeah, I think you or the others. You have asked something, right? About from complex analysis question. You or some other. I forgot the name. Not me. Okay. Someone has asked something. Okay, let me do it. So I think the question was that you have to find the integration over some contour C of tan z by z, right? So where C is the contour basically, all such z in C such that mod of z minus 1 equals to, I think, 2. Yeah. So you have to basically, this you can do by residue theorem, right? Cauchy's residue theorem. So for that you have to find what are the poles inside this contour. So what is this contour? So let's call it this point to be 1. Then you have to take a circle of radius 2. So what are the poles for tan z by z? Tan z by z, it is basically sin z by z into 1 by cos z, right? So pole means you have to find where this function will vanish, right? So to find what this function will vanish. So note that z equals to 0 is not a singularity because it is removable singularity, because limit z tends to 0 sin z by z, this, because real limit exists, so therefore if this limit exists then it is not the singularity, basically it will give the value 1. So 0 equals z equals to 0 is not a singularity, is not a actual singularity, is not gives us any pole type of singularity, is removable singularity. So therefore all the singularity will come from the cos z, right? So where will cos z can be 0? So cos z means basically this is cos of x plus iy, right? So what is this? This is basically, if you expand it in terms of formula, cos x cos hyperbolic y minus I sin x sin hyperbolic y. So if we put this equals to 0, means real part and imaginary part both have to 0. So when note that cos hyperbolic y is always strictly positive. So this is always strictly positive, and this is not, and sin hyperbolic y is 0 if and only because this is a strictly increasing function y equals to 0. Yeah, so basically I am saying that cos hyperbolic z can be 0 for only the where the cos x is 0, right? So basically when this will be 0, but in this part when cos x is 0, because this cannot be 0, so only cos x can be 0 for x equals to 2n plus 1 into pi by 2, but then sin cannot be 0, and y, this part can only be 0 when y equals to 0. So cos z is 0 if and only cos x equals to 0 and y equals to 0. So cos x equals to 0 means x equals to 2n plus 1 into pi by 2, and y equals to 0 means only singularity are for the real values, right? So now let's see for n greater than equals to, I think, 0. So what are the n belongs to z, I think, right? Yeah. So now which values are lying inside this contour? So only you can see that pi by 2 is the only singularity. So pi by 2 is only inside C. So only singularity is the at pi by 2. Right. Something here pi by 2. Minus pi by 2 is not inside this contour. So you have to then by Cauchy's residue sums, this will be the 2 pi I into this residue at the point pi by 2. So integral of over C tan z by z, it will be 2 pi I into residue of this tan z by z at the point pi by 2. And what is this residue of tan z by z at the point pi by 2? Note that at pi by 2 cos z has only 0 of order 1. This you can show at pi by 2. This does not have a zeros of higher order. So basically it has a pole, simple pole at pi by 2. Also note tan z by z has simple pole at z equals to pi by 2, because cos z has a simple 0 at z equals to pi by 2. This you can easily check. So therefore what will be the residue? Residue of tan z by z at the point pi by 2, it will be basically limit z tends to pi by 2 z minus pi by 2 of tan z by z, right? So now you have to find what will be this limit. Basically in complex form you can also use L'Hopital rule, but let me do it otherwise. So basically this z minus pi by 2 into sin z by z cos z. Note that at z tends to pi by 2 sin z is basically 1 sin pi by 2, and this has also no problem, so we can take the limit. So basically it will be, basically we put 2 by pi and whatever is the remaining limit z tends to pi by 2 z minus pi by 2 by cos z. So basically you have to find only this limit. And note that cos z, now cos z has only simple pole. How to check? Simple 0, that we have said earlier. So cos pi by 2 is 0, and now as cos pi by 2 is 0, so therefore you can write cos z basically z minus pi by 2 times some function gz, right? Now what will be this gz? So this you can write. So therefore, and you have to find what will be the value of at the point g pi by 2. So differentiate this one both sides, then you will get minus sin z equals to z minus pi by 2 g dash z plus gz, right? Now put z equals to pi by 2, then you will get minus 1 equals to gz, g pi by 2. So g pi by 2 has value minus 1, right? So therefore, so this one and this one also. So therefore just write this one as 2 by pi into limit z tends to pi by 2. So z minus pi by 2, and how we have written cos z? Cos z we have written basically this form. So put it there, z minus pi by 2 into gz. Now this will cancel out, so basically you will get limit z tends to pi by 2 1 by gz. And what is g at pi by 2? So from this, g of pi by 2 is minus 1, so this will be basically 2 by 2 by pi into minus 1. So therefore it is minus 2 by pi, right? So you have get residue equals minus 2 by pi. So by Cauchy's residue theorem, therefore this will be minus 2 pi I into 2 by pi, so it will be minus 4i. So this will be the answer. Yeah, any question or doubt with this one? This is the question basically. Okay, any question or any other question? Okay. So in the next class we will solve question from algebra, two problem from algebra. Okay. So if there is no other question, then we can, I think, stop. We can meet in the next next week, same time. Yeah. Thank you.